How's your weekend, Professor?
Weekend was good. Yeah, I organized a lot of my apartment, so I did a lot of cleaning. So um, it's always the post cleaning feel is always really good because now I can find everything.
Found did you were able to find like a $20 bill in the between the couches?
Oh, actually more than that. So it was because we had a lot of like we had just had a lot of random boxes still because when we moved at the beginning of the year, and finally I kind of just organized everything. I found yeah, a lot of loose change that we thought we had lost. So it was uh it was a good day.
That was good. I was helping my family rototilling the our backyard for the garden yesterday.
Nice, nice.
I was breaking up the dirt so that my it was easier for my dad to rototill.
Nice, nice, cool. Yeah, I'm excited for when I have my own house and I can do garden work because it's something that I always helped my grandma with growing up, and so it's it'll be nice to have a yard, but I've just settled for just potted plants for for the last several years of my life.
Yeah. Definitely, I would say definitely look make sure you do like look up for like the different type of plants. The reason being is that my mom she got loofah sponges, which is like a vine type plant. They're very aggressive and they produce a shit ton of seeds.
Oh wow.
And one the yeah, because like one seed yielded I think like a 2 bags full of seeds or something like that.
Oh wow.
And the other kicker is that yeah, because it's a loofah sponge, so the idea is that you dry it out and you tear off the skin, and that will be a sponge you can use for dishes and whatnot.
Oh,
The
that's
um
cool.
the things that don't put them, make sure they're on hard surfaces and don't put them in the garden or anywhere there's dirt,
Hmm.
because the seeds will kind of I guess spit out and will plant themselves in the garden. Because there's
Right.
my mom did that and it filled like it took over the garden for a little bit.
You have a loofah sponge army in the backyard.
Yeah.
Okay, it's 2:30, so let's go ahead and get started today. All right, good afternoon, everyone. It's the week, we're in week 9, so just one more week to go, and then we have spring break, and so we'll have at least a little bit of a break. And so, how's everyone doing today?
A little bit hungover, but ready to learn.
That's good. It's a little bit early, but I mean, a week early to be hungover, but glad you. Seems like you had a fun weekend.
A little sore from yesterday.
Oh, I bet. Yeah. Yeah, college basketball, it's exciting this year. So I did my college at UCLA, and so I'm naturally biased to rooting for them. And like they've been playing great so far. Seems like all of the Pac-12 seems to be pretty underseeded just because they just all kind of beat up on each other in the conference, and so their records don't indicate how good they are, but like they've been doing really well. Yeah, Hawk is crazy, man. The game against Michigan State, he played his brains out. It's crazy. Um, okay, and so the plan for today is we're going to continue on with our lecture notes on internal convection. Okay, and so I'm hoping to get most of it done by today. Just so that we can start another set of lecture notes on Wednesday. But depending on how fast we go, we might not get there. Okay. And so a reminder, we have homework 4 that's to do this Friday. And so homework 4 doesn't have anything to do with internal convection. And so it just has to do with external convection. And so you should have everything you need to do that homework. And so if you're working on it and you have any questions, definitely, don't be afraid to send me an email, come to office hours, so I can help you out with that. Okay. All right. And so are there any questions I can answer before we get started today? Okay. All right.
Did
So
you
let's go
say
ahead.
homework 4 was next Friday or this Friday?
This Friday. So it's going to be due before the spring break. Mhm. Okay. So let's go ahead and get started. And so we're working on internal convection. Right. And so this is kind of our second big unit in this our second big topic in this big unit on convection, right? And so by internal convection, remember what I mean by that is basically flow situations where we have the fluids confined by walls on all sides. Okay. Okay. And so we have a situation like this. We have flow coming down the middle, right? And what's unique about this is the flow is contained on all sides, okay? And so the biggest difference that we saw is that when we're formulating our amount of convection heat transfer, we do it in terms of the mean temperature instead of the free stream, right? And so when we write out Newton's law of cooling, and so we have Q is equal to HA Ts minus T infinity, right? And so this is what we usually have for convection, but what we said for internal convection was that instead of T infinity right here, what we have instead is Tm. Okay. And what's unique about this Tm is that this is basically the mean temperature in the cross section. Okay. And so basically what that means is that, say that we have a circular pipe here. And so if I draw kind of a cross section just like that, okay, Tm would basically just be the average pressure across that cross section, okay? And at first, this might just seem like just a notational change. And so instead of an infinity sign, what we have is an M. But what we said was that, because the flow is confined here, and because we have just like a finite amount of fluid, this Tm is going to evolve going down the pipe. Or in other words, it's going to change. Okay. And the reason for that is because we have such a confined space, as heat gets exchanged between the fluid and the walls, right? So let's say that, we have heat coming out here, okay? And so as heat is lost, that actually affects the overall internal energy of the system. And it's actually pretty significant because we have just a small amount of fluid there, okay? And so the first thing we're going to do today is we're actually going to talk about a way that we can actually solve for expressions for Tm, okay? And so what we actually are going to get are the mean temperatures as a function of x, right? Where x is the direction down the length of the tube, okay? And so basically what we'll see, and we'll have to apply some assumptions in order to solve for this, just because it's a little bit difficult to solve otherwise, that under some assumptions, we'll be able to solve for how the mean temperature changes along the length of the pipe. Okay. All right. And one last thing that I want to kind of remind you from last time is that even though our mean temperature here is changing, our convection coefficient H is actually going to be a constant. This point won't come up until later, but it's kind of good to kind of note it right now. And so what you'll see later on is that our expressions for like the Nusselt number is going to be extremely simple. And so it's going to be a lot simpler than, than external convection. And so for internal convection, what you'll see is that the difficulty is a little bit, it's different than external convection, because for external convection, we had those kind of sophisticated, kind of complicated expressions for the Nusselt number. For internal convections, our Nusselt number correlations will be really simple, but the mean temperature will be a lot more difficult to calculate by comparison. Okay. All right. Any questions on this? This is just kind of a recap from last time. Okay. All right. And so let's go about determining expression for the mean temperature. Okay. And so basically what we're solving for here, or what we want to determine, is an expression for Tm as a function of x. Or in other words, how the mean temperature evolves as we travel along the pipe. Okay. And so for this, I'm going to do just a short derivation. It's very short. So normally I don't like doing these, but this one's pretty short. Okay. And so what I'm going to do is I'm going to draw a pipe that we usually have. Okay. And then let me draw a control volume, albeit a very tiny control volume. Okay. Okay. And so remember, control volumes are just tiny regions in space under which we can form our conservation laws. Okay, and so in this case we're going to form a conservation of energy on this tiny parcel of fluid. Okay. Okay. And so let me define some things in this diagram here. So first thing we're going to have is, of course, since it's convection, we're going to have a flow of fluid down there. So, our fluid's going to be moving. And the way I'm going to characterize that fluid is with m dot, where m dot right here, this is going to be the mass flow rate of the fluid going down a pipe. Okay. And so the units for mass flow rate are going to be mass over time. And so like typical SI units for this would be kilograms per second. Okay. Right. I don't believe we've defined fluid flow in terms of mass flow rate before, so I wanted to make sure I define that. Okay. All right. So let's define the amount of heat that's coming in. Okay. And so we'll assume that the only heat transfer that we're going to consider is from convection. Okay. And so let's assume that convection goes into the fluid. Okay. And I'll call that amount of convection heat transfer dq conv. Okay. Right. And so the last thing that we're going to need is the length of this parcel. And so let's define this length right here to be dx. Okay. Okay. And I'm using the d's here, so I'm using like dq and dx here just to denote that this is kind of a tiny parcel. Okay. So tiny that it's I'm kind of drawing it as a square here, but in reality it's something that's really, really small. Okay. Okay. And so when we apply conservation of energy, basically what we're saying is that when we have convection heat transfer into this fluid, it's going to cause a change in the mean temperature of the fluid. Okay. Okay. And so you can think of it almost as like, when we add heat, or when we heat up this little parcel of fluid, then its internal energy is going to go up. Okay. And so what we can basically form from this is an equivalence, right? And so on one side, we can have dTm, okay, where this dTm right here, this represents our change in mean temperature. Okay. And then what we're going to do is we're going to multiply this in order to change it into a heat transfer rate. We're going to multiply it by the mass flow rate and the specific heat of this fluid. Okay. Okay. And so I'm just taking basically just temperature or delta T, you can kind of think of it like that, and multiplying by m dot Cp. And then what that's going to do is it's going to convert it into a heat transfer rate. Okay. And so the reason we want to do that is we want to relate it to dq convection. Okay. And so by conservation of energy, what we say is that this increase in internal energy of the fluid has to equal to the amount of heat that comes in. Okay. Okay. Right. And so, you know, the key to this expression here is this equal sign, right? And so what that equal sign basically says that, you know, whatever heat that we put into the fluid, you know, is going to cause its internal energy or its mean temperature to go up. Okay. All right. And then one more equivalence that we can put here on this right-hand side, we can formulate this dq convection in terms of Newton's law of cooling, because that's an expression that we know. Right? Okay. And so by Newton's law of cooling, what we can say is that Q convection here is going to be equal to H, which is our convection coefficient, times the surface temperature minus the mean temperature, right? And since this is acting on just a tiny parcel of fluid, we're going to multiply it by dA, which is the tiny area, okay? And so remember TS is just whatever temperature is on the surface, so we'll call that like that, okay? And Tm, of course, is our mean temperature, which is what we're ultimately going to solve for. Okay, any questions on this?
What is the CP multiplied to m dot?
CP is specific heat.
Ah, okay.
Mm-hmm. Okay. All right. And so let's work with just kind of the leftmost expression here and the rightmost one. So we're going to basically cut out the middleman. And so we're going to set this left-hand side equal to that right-hand side. Okay. All right. And so on one side of the equation, we have m dot Cp dTm is equal to H times Ts minus Tm times dA. Right. All right. And so from this expression, let's simplify dA a little bit. And so dA, what this represents here is this is the surface area over our little parcel of fluid. And so another way that we can formulate this is we can say that dA is equal to P times dx, where P right here, hopefully this looks familiar from when we did our fin stuff. This P is just the perimeter around the parcel. Okay. And of course, dx is just the length of the fluid parcel. Okay. Right. And so if we plug all that in, what we get is m dot Cp dTm is equal to H Ts minus Tm times P dx. Okay. And then from here, what we can do is we can simplify this expression. We can do kind of like a pseudo derivative. I know this isn't how derivatives are born, but you know, we'll assume we'll suspend our imagination a little bit. The derivative stork fairy came, or whatever you want to say. Okay, and so we'll divide both sides here by dx, And then we'll divide both sides by m dot Cp. Okay? So I'm going to just basically take this whole expression, divide by dx times m dot Cp. Okay. And then what we get is kind of a deceptively simple differential equation here. The parcel is the box. Yes, yeah. So the parcel of fluid is basically just this box that I drew on the previous page right here. Yeah. So it's like almost like an imaginary box that we're putting around like a small parcel or a small amount of fluid. Mm-hmm. Okay. And so we do that division and we end up with dTm dx is equal to HP divided by m dot Cp times Ts minus Tm. Okay. Right. And so this equation right here, this is our evolution equation for the mean temperature. Okay. And so it looks, not that bad. And so what we have is just a first order derivative, and on the right hand side, we have just some stuff there. Okay. Let me clean up this parenthesis a little bit so it kind of looks like a C. Okay. It's not that much better. Okay. And so in order to solve for the mean temperature, all we have to do is just solve this differential equation. But unfortunately, it's a lot easier said than done because, even though everything I have outside the parentheses here, so we have H, we have P, we have M dot, and we have Cp, all these guys are constants. Okay. Okay. And so those are fine. And so, we don't usually have to worry about those things. Okay. What we have to worry about actually are these two. Okay. Ts and Tm. So remember, Ts is the surface temperature, or it's the temperature at the surface of our pipe. And Tm is, of course, our mean temperature that we're trying to solve for. Okay. And so the reason these are complicated, this is more complicated than it seems, is that Ts and Tm are both functions of x, or they depend on x. Okay. And so basically what that means is that, as we go along, or as we ride along in the pipe, both the mean temperature and the surface temperature, they're both going to change. And so since we have both of these changing at the same time, we can't just straight up solve this equation for Tm because it's going to be a bit more complicated. And so at this point, we have to make some assumptions in order for us to solve this equation. And I'll give you basically two. I'm basically going to show you how to solve this in two common situations that you'll find in practice. Okay. All right. Any questions on this so far? Okay. All right. And so let's go over some situations where we can actually solve this equation. Okay. And so the first situation that we'll look at is when we have constant heat flux coming from the wall. And so what that means physically is that, as we go along the vessel wall, then we have a basically constant amount of heat transfer that's occurring from the wall. Okay. Okay, so we have our pipe right here. Okay. And if we measure the amount of heat transfer that's coming from the wall into the fluid, it's going to be constant. Okay. Right. And so all the red arrows there basically represent the amount of heat or the heat transfer that's occurring from the walls into the fluid. And so in this situation, Q wall is constant. Right? And in another way that we can express Q wall here, okay, or in other words, we're going to express it in terms of the heat flux. Okay. Right. What we can say is that this is going to be equal to H times Ts minus Tm. Okay. Right. Because that's basically just the convection heat transfer from the wall into the fluid, okay, in terms of flux. And so if you notice, the area here is missing because I put it in flux form. So that's why I have kind of the double primes. And this has to be constant under this assumption. Okay. And so if we relate this back into our previous equation here, what we can do is we can take this H times Ts minus Tm and just set it equal to Q wall. Okay. All right. And so if we plug that into our previous equation, what we have is dTm dx is equal to P divided by m dot Cp. Okay. And if we plug in for H times Ts minus Tm, then all we get there is just Q wall. Okay. Right. And so at this point, what we have is just, just dTm dx is equal to P, which is a constant, divided by m dot, which is a constant, divided by Cp, which is a constant, multiplied by Q wall double prime, which is a constant. And so this whole thing right here is just a constant. And so since this whole thing is a constant, we can just integrate both sides. Okay. Okay. And so what we get is Tm of x is equal to P Q wall double prime divided by m dot Cp times x. Okay. And of course, because we're just performing an indefinite integral here, we have to add a constant. Okay. And that constant is just our constant of integration that comes out. And so for these kinds of equations, typically how we solve for this constant is we set it equal to the mean temperature at x is equal to 0. And so this Tm of 0 here is the mean temperature at x is equal to 0. Okay. And so we have just a simple linear function here. Okay. And so what this tells you is that when you have constant heat flux, then the mean temperature is just kind of linearly rising. So it's basically steadily rising as you go along the pipe. Okay. All right. Any questions on this? Okay. All right, so let me just draw a quick graph for you just to kind of show you what it looks like, and then we'll do an example. And so let's say that we have a graph here, and then on the x-axis we have x. Okay, where x, remember, this is going to be our distance along the pipe. And on the y-axis right here, we're going to have temperature. And so if our graph is linear, basically what this means is that as a function of x, our mean temperature is just going to look like that. Okay. It's just going to keep just linearly increasing. Right. And then right alongside this, because our heat flux is constant, then that means our surface temperature also has to go up as a function of x. And so our surface temperature usually looks something like this. And so it's usually right alongside Tm, and it has the exact same slope. Okay. Okay. And so basically the difference in between these two curves, has to be the same all throughout, because that's what's going to give us our constant heat flux. Okay. And so even though, I know we only solved the equation for Tm, but, just the fact that we have a constant heat flux also implies that Ts also increases linearly by that same rate. Okay. And the distance in between those two depends on how much heat flux that you have coming out. Okay, and so let's do an example of this, just so you can kind of see it in action. And what you'll see from this is that, for cases where you can actually solve for the mean temperature, you can actually use that to solve for H as well. Okay. All right, so let's look at this example where we're going to look at a water heater. Okay, and so this water heater is basically going to be responsible for heating up water from 20 degrees C up to 60 degrees C. Okay. And so schematically, it's going to look like this. And so I'm going to assume it's basically just one long pipe. Okay. And so on the left-hand side, which is where we'll call this the inlet, we'll say that the mean temperature here, that's going to be 20 degrees C. Okay. And then by the outlet, or by the end of the pipe, we're going to heat it up to 60 degrees C. Okay. All right. And so let's put some other stats in here. And so let's say that we have a mass flow rate of 0.1 kilograms per second. Okay. And so that defines basically is how much fluid is coming down. We're going to assume constant heat flux. And so the heat flux is going to have the following value. Okay, so let's assume that Q wall here is going to be 1.5 times 10 to the fourth watts per meter squared. Okay, and so that's going to be our Q wall. And then for part 2 of the problem, we also are going to assume that we know the surface temperature as well. Okay. Actually, let me draw this a bit more accurately. And so let's say that we know the surface temperature at the outlet. Okay. Okay, so we'll call that TSO, and then we'll say that this is 70 degrees C. Okay. Okay. And then last thing we need is just the tube diameter. And so let's say that the tube diameter here is going to be 20 millimeters. Okay. All right. And so for under this configuration, let's solve for a few things. And so first thing we're going to solve for is what is the length of the tube required in order to achieve these conditions. And so we're basically going to be solving for the length of tubing. Okay. And in part 2, we're actually going to use that, our solution from part 1 to solve for the convection coefficient H. Okay. All right. Any questions on the problem setup? Okay. All right. And so let's go ahead and start solving it. So part 1, what we want to solve for is we want to solve for the length of tubing required. Okay. And so in this case, since we have, since we have a constant heat flux, let's use our TM expression from before. Okay, and so here we have Tm of x is equal to Q wall double prime times P divided by m dot Cp x plus Tm of 0. Okay. All right. And so in order to use this tape, or in order to use this expression here, we need to look up the specific heat for water. Okay. Right. And so let's look this up in table A.6 in the book. Okay. And of course, remember, whenever you're evaluating properties in a table, you have to specify which temperature that you're solving this at. And so, in this case, just like we usually do for the film temperature, we usually take it, as an average of our two temperature extremes. And so our two temperature extremes here in the fluid are going to be it's going to be 20 degrees C and 60 degree. And so what we can say is that our film temperature TF is just going to be the average between the two. So it'll be 20 plus 60 divided by 2 is equal to 40 degrees C. Okay. And so we're going to evaluate our properties at that. And then what we get is Cp is equal to 4,179 joules per kilogram K. Okay. And so now we have, we have everything that we need to plug into this formula. And so if we plug in for Q wall, which is given to us in the problem, perimeter, we can easily compute that from the diameter of the pipe, and m dot is of course given to us in the problem. What we get is Tm of x is equal to 2.255x plus Tm of 0. Okay. And so, just in order to get that 2.255, all I did was just like plugged in the variables from the problem. Okay. All right. And so what we're solving for, remember, in this case is the length, right? And so ultimately we're going to solve for some x here. And so before we do that, let's specify Tm of 0. And so our Tm of 0 is just whatever the mean temperature is at the beginning of the pipe. And so in this case, the beginning of the pipe is at a temperature of 20 degrees C. Okay, because that's on kind of the leftmost side. Okay. And then, now that we set that to 20 degrees C, what we can do is we can set this entire expression, or set Tm of x equal to 60. And then, we set Tm of x is equal to 60. And then what we can do is we can solve for the x in order to make this happen. Okay. Because remember that x, what that represents is distance along the pipe. And so, the x is basically going to be the length of tubing that we need to satisfy this requirement. Okay. All right. And so let's go ahead and do all that. And so for Tm of x, we're going to plug in 60. We have our 2.255. And since, we're solving for a length, and so I'm going to change x to L. Okay. And then all this is going to be equal, or all this is going to be added to 20 degrees C. Okay. Then from this expression here, we can just solve for L. And so L is just going to be 60 minus 20 divided by 2.255. Okay. And so what this gives us is 17.74 meters. Right. That's a pretty long pipe. And so under these conditions, basically, you need to have a pipe that's almost 18 meters long. And so that's pretty big. Okay. All right. Any questions on how we did this part? Okay. All right. And so that's part one. And so part two of this problem, we want to solve for H. All right. And so to do this, we're just going to use basically Newton's law of cooling, because we know what the mean temperature is, we know what the heat flux is, and we know, what the surface temperature is. And so all we have to do is just plug this all in and solve for H. Okay. Right. And so what we have is Q wall double prime is equal to H times Ts minus Tm. Okay. And then in order to basically use this to solve for H, we need to evaluate both of these temperatures, Ts and Tm. They have to be evaluated at the same value of X. Because remember, as we go along in this pipe, both the mean temperature and the surface temperature are constantly increasing, okay? And so in order to basically make this comparison, and you're going to subtract the two, they have to be at the same location, okay? And so for this particular problem, since we only have the surface temperature at the outlet, let's evaluate these at the outlet. Okay. And so we go ahead and plug all this in. We know that Q wall here, Q wall is 1.5 times 10 to the 4th watts per meter square. Okay, and so all that's just from the problem. And then we have H, and then we have the surface temperature here at the outlet. And so from the problem, what I have written in orange right here is we said that the surface temperature at the outlet is going to be just 70 degrees C, right? So we have 70 degrees C minus the mean temperature at the outlet, which we know is 60 degrees C, right? And so what we get from this is an H value equal to 70 minus 60 divided by 1.4 times 10 to the 4th, okay? And then what we get from that is, it's the reverse. So we have 1.4 times 10 to the 4th divided by 70 minus 60, okay? And then what we get from this is 1,500 watts per meter squared K. And so basically we have an expression for H, without having to, go through the Nusselt numbers, which is nice. And so for the cases where you can solve for the mean temperature like this, you don't need to go and do a Nusselt number correlation at all. Okay. All right. Any questions on this example here? My eyes are straining right now, so let me go turn on the light real quick. I understand why people do dark mode now. So I don't like turning this light on. This is a new light because it gets really hot, but my eyes are kind of straining looking at the screen. I've had a lot of people call me a madman for using light mode for all of my apps and all that stuff, but I can understand why now because my eyes are starting to hurt a little bit looking at these screens. Okay, so no questions on this problem. Okay, and so let's go over the next situation where we can solve for the mean temperature now, which is constant surface temperature. Turn on blue light filter. I'll have to give that a try next time. Yeah. I've also seen people wear like the gamer glasses, like which are basically the yellow sunglasses things. Which I theoretically, I like the idea of that, but like they're really expensive. I found, which is way too much for that.
You can find some cheap pairs, but personally, like when I wear them, I don't know, they almost make my like eyes hurt more.
Oh dang, I see.
I also wear glasses as well, so wearing two glasses at once kind of sucks.
Oh, I see. Yeah, that makes sense. Yeah, it's always a difficult thing. Oh yeah. I used to have an app on my or I used to have a program on my laptop called I forgot what it's called, but basically like it kind of dimmed the entire screen to make it more bearable. And so like back in college when like I would play like League of Legends with my roommates until like 3 o'clock in the morning. That's we needed that to save our eyes. It wasn't successful, so my eyes are terrible now because I did that in college. But those were kind of the fun days. Okay, and so let's return back to our evolution formula for the mean temperature. Okay. And so we have dTm dx. And this is equal to P times H times m dot Cp times Ts minus Tm. Okay. And so previously what we did was we assumed that this quantity H times Ts minus Tm was constant. And so that was a constant heat flux case. And so now what we're going to assume is that now this Ts here is going to be a constant. And so just Ts. Okay. All right. And so now what we have is basically dTm dx is equal to pH over m dot Cp times constant minus Tm. And so to help us out with this, we're going to bring back an old friend, or maybe an old thing that you hate, depending on your perspective. But we're going to introduce our excess temperature here because we have basically, mean temperature minus Ts, which is constant. And so let's say that we have theta is going to be equal to Tm minus Ts. Okay. So this was our excess temperature. Okay. And so if we introduce that into this equation, we basically can plug in for this guy here. I flipped it on purpose so that we get a negative, and that's by design. Okay. And remember, when we have this expression like this, we can take d theta dx, okay, and this is equal to dTm dx minus dTs dx, right? But since our surface temperature here is a constant, when we take the derivative of a constant, we just, it just goes away. Okay? And so if we make the substitution in for the left-hand side and then the substitution for theta on the right-hand side, what we get is d theta dx is equal to minus p times h divided by m dot Cp times theta. And so basically now we have this, first order differential equation and we can solve it. But it's not a constant because, we have this theta on the right-hand side, okay? And we have d theta over here. And so we can't simply just integrate this. The way that we need to solve this is by separation of variables. Okay. And so I'm going to divide both sides by theta. And so on the left-hand side, we'll have d theta over theta. And this is equal to minus pH divided by m dot Cp dx. Okay. And then now that we have it in this form, we can just simply integrate. Okay. And then what we get is ln of theta is equal to minus pH x divided by m dot Cp. Okay. Then we're going to take the exponential of both sides. And I'm going, kind of quickly just because, we've kind of seen this before. Okay? And then what we get is theta of x is equal to theta 0 times exponential. I'm going to use this exp, symbol here just because it's, we have a lot in the exponent here, times minus pH divided by m dot Cp x. Okay. Right. And so that's our expression here for the excess temperature, but we're going to take this kind of one step further, and then we're going to turn this back into an expression for Tm of x, just because that's a little bit easier to work with in practice. Okay. Right. And so I'll do that on the next page. And so on the next page, I'll basically give you the formula that you can use for a constant surface temperature. Okay. All right. Any questions on this?
Just specifying, you said that's all in the exponent, correct?
Yes. Yeah. Yeah. So I'm using this exp basically. Whenever you see this exp right here, basically what that means is that everything in the brackets next to it is raised, raised to the e. Yeah.
Gotcha. Okay. Thank you.
Mm-hmm. Yeah, if you're using MATLAB too, there's no MATLAB in this class, but that's basically how you type in the code for exponential. You do exp and then parentheses, all of that stuff, and that does e raised to all of that power. Okay, and so let's go ahead and make the substitutions back. Okay, because remember theta of x, what this was equal to Tm of x minus Ts, which is a constant. Okay. And then theta naught, that was the constant that's out in front. This is our initial, excess temperature at the beginning. Okay. And so the way we can express that is Tm of 0 minus Ts. And so this is our initial excess temperature. All right, and so we make those substitutions back, and then what we get is Tm of x is equal to Tm of 0 minus Ts times exponential times minus pH divided by m dot Cp x plus Ts. Okay. And so this right here is our evolution of the mean temperature when we have a constant surface temperature. Okay. All right. And so since this is a decaying exponential, our graphs are going to look kind of like the following. Right, and so the graphs look something like this. Okay. And so I'm going to draw you two cases here. Okay. And so there's a case where the fluid is being heated by the wall. Okay. And so basically in this case right here, Ts is greater than Tm, okay? And so the surface temperature is hotter than the fluid, and so the fluid is going to basically be heated, okay? And so this dotted line that I drew here, this is going to be Ts, which is, you know, a constant in here in this case, okay? And then our graph is going to look something like this. And so this is Tm of x. Okay. And this is when fluid is being heated. Okay. And then conversely, for the other situation, we're going to assume that Ts is less than Tm. Okay. And so basically, we have a cooler surface than we have our fluid. Then our fluid is going to be cooled now. Okay. And so on the bottom here, I have my dotted line, which is going to be Ts. And so our graph is going to look something like this. Okay, so fluid, in this case, is being cooled. Okay. And so, you know, it doesn't matter, you know, if the fluid's being heated or it's being cooled, you have this kind of decaying exponential relationship. Okay. Okay. Any questions on this? All right, so I'll do an example with constant surface temperature a bit later, but there's one more thing that I wanted to cover before that, which was actually our Nusselt number correlations. Okay. Okay. All right, and so in order to do that, what we need to do is we need to solve for the temperature profile or the temperature distribution in the pipe. In other words, you know, what we want to find out is how the temperature actually varies in a cross section. Okay, because so far what we solve for is how the temperature varies, you know, along the pipe. Right. So if I draw our pipe like this, okay. Okay. What we solve for so far is how the temperature varies in the x direction. Or the x direction is basically, you know, down the length of the pipe. But in order to actually get an expression for the Nusselt number correlation, what we need is actually the temperature distribution in this direction, in purple, okay, which is the r direction. Okay. And so doing this, you know, from this basically we'll be able to compute. Basically, our goal is basically the derivative of the temperature distribution in the r direction. Okay. Because from this dTdr, then what we can actually use this to solve for the Nusselt number correlation. So kind of if you think all the way back, you know, I think, you know, maybe 2 or 3 weeks ago, we had kind of our first expression for the convection coefficient, which involved, you know, this derivative right here. Okay. And so, you know, by solving that, we can actually do that. And for internal flows, relatively speaking, it's not that bad. but it's still pretty bad. And so I'll kind of spare you all the gory details from this. And in case you're curious, I'll write out the equation that you can solve for from the book. I would never expect you to know this or to use it in a problem. But just to kind of show you what it looks like, and basically what you get is a fourth order equation. Right? And so let me go ahead and write this out. But again, this is you don't actually need this for anything. Okay? And so actually, let me write this out. So ... after lots of math. Okay. Right. And so that math being, more conservation of energy stuff. And so basically, the way the derivation goes is you draw kind of a small parcel of fluid, just like before. And then you basically form conservation of energy here. But now instead of just not only dx, we have a direction dr here as well. And that makes things a little bit complicated and a little bit tough to get through in the last 15 minutes of class. Right? And so if you do all that stuff, and you end up with the following expression. Okay. All right, so we get 2 um. So I'll write down everything first, and then I'll define all the terms. Okay, dt dx, dtm dx, I should say. All right, times r squared over 4 minus r to the 4th divided by 16 ro squared minus 3 ro over 16. Okay. I think that should be an ro squared. Okay. Plus ts. Okay. And so it's kind of a lot of math to get to this point. And so that's ultimately that stuff's not too important. But let me go ahead and define these terms for you here, just so you know what they are. Okay? And so we use the subscript m to denote basically the same thing. And so this is basically the mean velocity down the across the cross section. Next, we have alpha. Remember, alpha here is our thermal diffusivity. Okay. dTm dx is the evolution of temperature in the x direction. Okay. And so that that of course depends on whether you're assuming it's constant surface temperature or constant surface flux. Okay. And what you'll see is that that'll give us 2 different Nusselt number correlations on the next page. Okay. So this depends on wall assumption. Okay. And I believe the last one that we have defined here is RO, where RO is just simply the radius of our pipe. And so we have RO, that looks like that. Okay. All right. And so what we can do from here is we can basically manipulate this expression to give us our Nusselt number correlations for internal flow. Okay. Under the caveat that this is the next 2 correlations that I'm going to show you are only for laminar flow. And so we'll deal with turbulent flow a bit later, but we're going to start with laminar flow first, just because they yield very simple Nusselt number correlations. And when I turn this page and I write them down, I guarantee that you'll probably not believe me that they're this simple, but they actually are. Right? Okay, so any questions on this? Okay. All right, and so before I give you the Nusselt number correlations, let me just remind you of something that we mentioned at the very beginning of class, which was, in internal flow, our convection coefficients and our Nusselt numbers are constant. Okay. under the condition that we have laminar flow. Okay. And if you remember, laminar flow for internal flow basically means our Reynolds number is less than 2300. Okay. And this is Reynolds number based on the diameter of the pipe. Okay. And so we have a much lower Reynolds number threshold here for this. And so if you're going to use these Nusselt number correlations, make sure that you're laminar. Because there's a different Nusselt number correlation for turbulent flow, which we'll go over probably on Wednesday. Okay. And so if you can assume that you have laminar flow, we have two different Nusselt number correlations here. So one of them is going to be for constant heat flux. And so if you have constant heat flux and you have laminar flow, then the Nusselt number correlation is the following. Okay? And so we have NUD. Okay? As remember, NU, our Nusselt number is going to be H times D divided by KF. Okay? And then for, if you have all these conditions met, the Nusselt number is equal to a magic number. And that magic number is 4.36. Okay. And so it's kind of like the Hitchhiker's Guide to the Universe, which is the answer to everything. In this case, it's not 24, but it's 4.36, right? It's a very strange formula, and probably at this point, I know most of you guys are juniors or seniors, so you've seen all manner of really complicated, really sophisticated formulas, and so to have a formula just equal 4.36 is a little bit jarring, I'm sure, but that's what it is. Okay? And so that's for constant surface flux, and so our other condition, remember, was constant surface temperature. And so for constant surface temperature, we have a very similar expression. And so for constant surface temperature, NUD, which again is equal to HD divided by KF, okay? This is equal to 3.66. Okay. All right. So very, very simple expressions. Yeah. And so actually, last time I taught this, which was a couple of years ago, I actually went through the whole derivation to get this temperature distribution here. And so, it was kind of lengthy, took, maybe 20, 30 minutes. And then I got to this result here, and then everyone kind of left the lecture very upset with me. And so, I don't want that to happen this year. And so, I kind of skipped most of the unnecessary details, and I just skipped to kind of the good part here, which is Nusselt number is very simple to calculate here for internal flows. Okay.
I love simplicity, the better.
Me too. Yeah, life is complicated enough as it is. Okay. So any questions on this before we apply this to an example? Actually, let's I'm going to apply this to kind of the previous example that we did and show you how we can use it to compute H. Okay. And so let's return to our water heater example and use this Nusselt number correlation to compute H. Okay. And so if you recall from the previous example, what we had was a case of constant surface flux, right, or constant heat flux. And so under constant heat flux, we know that the Nusselt number is equal to 4.36. Okay. And this is equal to H times D divided by KF. Okay. And so we want to solve this equation for H. And so let's multiply both sides by KF over D. Okay. And so what we get is H is equal to 4.36 times KF over D. Okay. And so to evaluate this, we need to plug in KF for water. And again, we're going to evaluate this at the temperature of 40 degrees. Okay. And what we get is a KF is equal to 630 times 10 to the minus 3 watts per meter K. Oops. Okay. And if you recall our diameter was just 20 millimeters. Okay. And so we convert that to meters. We divide by 1,000, and so we have 0.02 meters. And then what we get from this is 137.34 watts per meter square. Okay. Okay. And so a lot easier than relatively speaking, for a lot of convection problems. Okay. Right. But wait, if you're looking back kind of at our previous example, what you saw was that the H that we previously found was not even close to this. Okay. And so from before, okay, what we found from just the mean temperature equation was that H was actually equal to 1,500 watts per meter squared. Okay. Okay. And so these guys are not even close. Right. And so what's the deal here? And so someone must be kind of messing with us here, because it's there's both methods here, both the Nusselt number method and the method where we use the mean temperature distribution. Both of those are valid, and so how are we getting such different answers here? Okay. And the reason we're getting different answers is that, remember, in order to use this simple Nusselt number correlation here, our big assumption was that our flow was laminar. Okay.
So if it doesn't match up, then it might be turbulent then?
Exactly, yeah. And so in this case, because the H that we found, from the mean temperature way was much higher, then this probably means that our flow was turbulent. Okay. And what do we know about turbulence is that, when you have turbulent flow, you have a much higher Reynolds number, and you have all this kind of chaotic mixing and all that stuff going on. And so that's going to lead you to a much higher H than what you do for a laminar flow situation. Okay. And so, if, these Nusselt number correlations are nice when you can use them and we have laminar flow. But, usually the more accurate way to compute them is actually going to be off the mean temperature distribution, which is what we used before. Okay. And so if you have the option to choose between the two, if you want to be safe, then you can use, I would use the kind of the mean temperature way, how we did it in the first example we did today. But, if you're able to determine that the flow is laminar, then you can use these very simple Nusselt number correlations for those. It'll save you kind of a lot of time and a lot of headache.
Are you able to give us an example of a way to test if it was laminar? Or
Yeah.
would it just be...
Yeah,
Okay.
So it would be just to kind of compute the Reynolds number for this. So
Okay.
I can do it really quick actually. So time's out, but because remember Reynolds number is going to be the mean velocity times the diameter divided by viscosity. Well, actually, I don't have the viscosity of water. So, but basically, the way that you can compute the mean velocity here is you can do it based off the mass flow rate, because we were given mass flow rate inside the problem. And so mass flow rate is equal to rho times A. Okay, and so you would solve for and so would be m dot divided by rho A. Okay, and so you'd plug that back in there. You'd plug in the diameter, and then you plug in for the viscosity. Okay, and this has to be less than 2300 in order for you to use the simple Nusselt number correlation. Okay? And so if you plug in actually everything from the previous problem, what you'll probably find is that this Reynolds number is much higher than 2300. But I don't have the viscosity of water at 40 degrees C in front of me, and I also don't have my calculator right now. So if you want to verify that yourself, you're definitely welcome to do so. But when we pick this up on Wednesday, I'm going to pick it up just basically from here. Okay. Okay.
Thank you, Professor.
Yep. Mm-hmm. All right. So any final questions before we wrap up for today? Okay. All right. So thank you guys for tuning in as usual. And so remember about homework 4 that's due this Friday. And so have a great rest of your afternoon, and I'll see you on Wednesday.
Thank you, Professor.
Thanks. Thanks, guys.
Thank you.
Thanks, guys.
Professor, could you go one page before that?
Yep. Mm-hmm.
One more page, actually.
Yep.
Okay, thank you.
Yep.
Have a great day.
You too. Nice. Yeah, they're up against like a 14 seed today, right? I mean, they pulled off a big upset too. Thanks. See you Wednesday.